All right, we're going to do a lab, so to speak, with standing waves, and we're going to do it with air in a closed pipe, closed on one end, and an open pipe, open on both ends. And we know that we can do a standing wave on a string, like with a musical instrument, like a guitar or piano or something like that. But we're also going to talk about standing waves in air, and so like a pipe organ or a flute or something like that. So if we were to do this lab at school, we would be using our LabQuest or our Chromebooks, a Vernier microphone sensor. We would have PVC piping for the first part. I'm just going to use one length. For the second part, a variety of lengths, but that's the second video. We will do a temperature probe just to find out the temperature, because we know that sound travels at a different speed at different temperatures. So for the first part, we're going to have one pipe length. We're going to have, this is going to be the pipe that's open on both ends. We're going to strike it with a finger so that it's open here and here. And we're going to set up a fundamental. So all of the things we'll set up are just the fundamental. For this, the pipe that's closed on one end, what we're going to do is bring our hand up, smack the bottom of it, and create that fundamental standing wave. But we're going to have a pipe then that's closed on one end. So I'll refer to this one as open on both ends. This one as closed on one end, obviously just one end. All right, so we know from the lectures that if we were to set up this standing wave on a string, what we would have here is we'd have an area of nodes, and we'd have an area of an antinode, the greatest amplitude here. Okay, and so we know we can set that up in a string, and then you know how to set up the second and the third and so on. Now what's going to happen with this is we're going to have our sound traveling in these pipes, and we know that sound travels longitudinally, meaning that the molecules of the medium travel in the same direction as the energy of the wave. However, what we're going to be measuring are areas of compressions or condensations, I mentioned that in the lectures, of areas that are more compressed, higher pressure, and areas of rarefactions which have less pressure. And so this is more transverse than longitudinal, but this is how we're going to measure this, or that's how the Vernier sensor does that. Okay, so as we go through here, I'll tell you exactly what you want to label on your paper, which would not be the same, of course, if we were actually together, but second best. So the first thing I want you to do, and definitely title it. It just doesn't have to be a standard type lab report. Title it as Standing Waves in a Column of Air. So number one, use the sketches that you find in, I think it was slide 28 in our notes, or you can Google it, and sketch the waveform for the fundamental mode of vibration in the air for an open tube. So here's our open tube. Sketch that. You can call that A. For B, how does the wavelength compare to the length of the tube? So what does the wavelength equal for B for a tube fundamental first harmonic for a tube that's open on both ends? And then C, I know it doesn't say this here, just label the antinode or nodes and nodes. Okay. So do that for ABC. So that's number 1, 2, and 3. All right, so for data, now I have to erase this as I scroll, so but you can always go back in the video. All right, so the data is going to be, we're going to set up a microphone, as you see here, smack the end of it with a finger so we don't close that end, so this is an open, okay? And we are going to measure the temperature. It's 25 degrees Celsius. A little warm for our school, but hey, that'll work for us. So set up a little data table. This isn't going to be number 2. It's just going to be a little data table that we'll set up. I'll get to the rest of the numbers. Measure and record the length and the diameter. For the length of the tube, let's go ahead and use 40 centimeters or 0.4 meters. And for a diameter, let's choose a tube that is 2.2, okay, 0.022 meters. Okay, so that's going to be our data. We're going to go ahead, smack it. The microphone is going to record that run. All right, and then you store the run, you do it a couple more times, and then you repeat this, but this time what you do is hit with your whole palm so that you're effectively closing the tube and having the microphone get that data. Okay, so some more stuff that we can put into the data table is a graph of the data that the microphone actually gives to you. So let's just quickly take a look at that. Let's see what we can do here. Like that. Let's look at these two pictures. Okay, so this is more data. So go ahead and add to your data table here. And you notice this is sound pressure versus time. And I don't know if you can, when I took a picture of it, scanned it, I don't know if you can really see that, so I'll rewrite it. But we're taking it from peak, 1, 2, 3, 4, 5 peaks. This is the tap and drag that you're so used to. And when you do that, it will measure those 5 peaks, the time. And, go ahead, and put down as your data 0.01283 seconds. And that is for 5 cycles or 5 wavelengths. Okay. We do want frequency, and frequency, if you recall, is cycles per second, not seconds per cycle. So I'm going to go ahead and divide that and flip it. And so I'm going to get 1 over 0.00257. And that is going to give me 389. And that is hertz, or 1 over seconds. Okay, so go ahead and jot that down for your data. The other thing I want to show you is another picture here that you can also choose from your data, and it's something called a fast Fourier transformation. Not sure how to pronounce that, but it gives you sort of a snapshot of sound frequency at a certain time. And you'll see that it pretty much agrees. We're looking at about 390.63 hertz. So 2 different ways that you can do that. So just say the FFT graph, we measured 390.63. So with the 389 and the 390.63, why don't we average that out for 390 hertz. All right, so what we've determined from the data is for the pipe that is open on both ends, okay, I'm just going to call it open, is 390 hertz for the fundamental, okay, and jot that down in your table. Now, I won't do the other 2 graphs, but for the closed pipe, it's doing that, for the closed pipe, if you did the same data here, you will get 213 hertz. So that's our data, 390 hertz for the fundamental on the open, and 213 hertz for the fundamental on the closed on one end. All right, so add that to your data table. Now we'll go back to this lab and talk about what else we need to do. So that's all of this stuff right here. All right, so we did all this. Okay, we got the second set, the 2. Okay, so we did 1 and 2. For number 3, it says to find the ratio of the frequency produced, and we're assuming the speed of the wave didn't change, our temperature didn't change that much. How does that compare? So I think what we'll do for the lab report then is you've stated the data from both of the graphs. You explain what the graphs are and how we got the data. Let's call that number 2. Wow. Okay, so for number 2 in your lab report, you're basically going to explain the data that we got. Basically my words for the past 2 minutes. Okay. For number 3, we're going to go ahead and take those 2 ratios and talk about them. So the ratios of the frequency are going to be 213 hertz. Okay, and kind of keep tabs. That was for our closed, okay, on one end, divided by 390 hertz, and that was our open. Okay, so that ratio is going to be a little more than half, 0.5 something something. So you do that. We would expect that because if you go back up and you, for a closed fundamental, what does that wave look like? What does your wavelength look like? How many L's is that? And for the open, how many L's is that? All right, so you've got half of the frequency for a closed versus an open. And I would like you just to make a statement in number 3 how that would make sense, because the open one is going to only, the wavelength will only be 2L, and the closed one wavelength will be 4L. So just make a statement regarding that. All right, well, it turns out we have a little bit more to do with that one. So I'll get this going here because we only have a few minutes left. So that was number 3. So for number 4, what I'd like you to do here is to, I guess it's the number 4 here. So number 4 and your piece of paper, I want you to sketch the waveform for the standing wave for a tube open on one end. Sketch that. That'll be part A. For part B, what fraction of the wavelength, what does that equal? Okay. And then it doesn't say it here, but label in node or nodes and antinodes. Okay. All right, we're going to make a couple of corrections here. Let me go through this pretty quickly. So for number 5, what I want you to do is a correction, because it actually turns out that the antinode occurs slightly outside of the open end. It should be a little bit longer. So we're going to add a correction to this. So what we're going to do here for 5, just call it 5A, is you're going to, for a closed, keep these straight people, for a closed one, you're going to do the effective length, and that's going to be our regular length of our tube, which is, of course, 0.4. And then we're going to go 0.33 times the diameter. Okay, and we wrote that down. And so that's actually our effective length. So if that's our effective length, rather than using L, let's use this, okay? And you can do this a little bit more direct, but I'm just going to go ahead and write this out. So if we've got a closed tube, we have our velocity there, it's going to be over 4L. Velocity of air at 25 degrees Celsius is 346. Now we are doing just ratios, so if you don't want to show that, you can show the ratio, that's fine. But now what we're going to do, so that's number 5. For number 6, what we're going to do is to do this for the tube that's open on both ends. Okay, oh sorry, this would be part B. Okay, for number 6, we're going to do this open at both ends, and if it's open at both ends, we're going to have to do 2 corrections. Open at both ends, okay. And so what you want to do here is do the effective is L plus 2 times 0.33 times the diameter. Okay, and that's going to be your part A that I want you to do here for number 6. And then for B, what I have to do here is to realize that this is an open, so the frequency is going to be the velocity over 2L. All right, so get those frequencies, and then for number 7, compare them. And I think you're going to get it, well, you're going to get a better number than that you did up in number 4. So if you compare now the frequency of the closed divided by the frequency of the open, what you're going to find here, and I would like you to do that, is closer to that true half value, 0.5 value that we should find. All right, so that's it for part 1.